In this video tutorial, we'll be looking at the dipole moment. Put simply, that is a measure of the polarity of a chemical bond, or alternatively, the overall polarity of a particular compound due to its molecular geometry. Before we continue on with this lesson, it is important that you are familiar with VSEPR theory. That's valence shell electron pair repulsion, as we will be referring back to the geometries learned in those lessons, especially when we start talking about the overall polarity of a molecule. So let's start with a quick review of electronegativity, En, which is the relative measure of an atom's ability to attract shared electrons in a chemical bond. If you recall, an atom's or an element's En value can be found in the periodic table. It ranges from 0 to 4, 4 being the highest attraction for electrons, and, well, there's no 0 here, but 0.7, for instance, very low on the scale, shows a very low attraction for electrons in a chemical bond. Electronegativity difference, on the other hand, symbolized by the delta En, provides us with a guideline to identify the polarity of a bond. Now, all of this was discussed in more detail in some of my prior videos, so if you're finding that a lot of this is somewhat unfamiliar, I highly recommend that you go back to watch my videos on chemical bonding, specifically those on ionic, polar covalent, and non-polar covalent. But moving on, if the delta En value is between 0 to 0.5, it tends to indicate that the atoms involved in this chemical bond are sharing their electrons fairly equally, resulting in a chemical bond that has non-polar covalent characteristics. On the other hand, polar covalent characteristics result from electrons that are shared unequally between two atoms. So that is indicated by a delta En value between 0.5 and 1.7. Finally, anytime you have a delta En value above 1.7, it tends to indicate that electrons are shared very, very unequally, almost to the point, well, in most cases, to the point where the electrons are being transferred from one atom to the other. So it's not really sharing anymore. It's a giveaway of electrons or a transfer of electrons. And that would be an ionic characteristic. Now, it is important to note that the delta En scale is more of a spectrum. So what I mean by spectrum is that, for instance, over here, I know this area is definitely yellow, but I don't know exactly where did the yellow begin and where exactly does the yellow end. Well, similarly, I don't know exactly where does polar covalent end and where exactly will ionic begin. So if I'm somewhere in this area around here, I like to call this the gray transitional area, you can't say definitively, oh, once you pass this border, it must be polar covalent or it must be ionic. Instead, you will likely have situations where you'll have a compound that's mostly ionic with some polar covalent characteristics, and vice versa. Thus, these numbers over here, 0.5 and 1.7, they are very arbitrary. In fact, our previous textbook stated that it was polar covalent was from 0.5 to 1.7, while our current textbook actually states 0.4 to 1.7 is polar covalent. And so for the purposes of this course, what we're going to do is we're going to assume a transitional gray area of plus or minus 0.1 of this border and this border over here. So anything in between 0.4 to 1.8 or so, we can safely say that the bond likely has more polar covalent characteristics than, say, ionic or non-polar. Let's take a look at the example of oxygen bonded to hydrogen. In this case, they'll be sharing electrons for stability. However, the question becomes, how will they share these electrons? Is it going to be an equal sharing, unequal sharing, or complete transfer of electrons? To predict this, we look at the delta En calculations, where we subtract the En values for oxygen and hydrogen, which are 3.5 and 2.1 respectively. We found these from the periodic table. And once we subtract them to find the difference, we see that's a 1.4. Now, 1.4 is well within the polar covalent range, so we can safely say that this particular chemical bond will have mostly polar covalent characteristics. And so the oxygen atom, with its higher En value, is going to hold on to these electrons more tightly to its nucleus than on the hydrogen. Thus, they'll spend most of their time orbiting around the oxygen and some of the time around hydrogen. This results in a partial positive charge for hydrogen and a partial negative charge for oxygen. Please keep in mind that delta En is an absolute value, meaning it's always positive, and so it does not matter which En value you subtract first, either 3.5 minus 2.1 or 2.1 minus 3.5. The important thing is this value small, medium, or large? Which corresponds to non-polar covalent, polar covalent, or ionic. So this migration of electrons from the hydrogen to the oxygen results in a separation of charge known as a dipole moment. Di meaning two, pole meaning opposite ends. So we have these two charges, these two poles, the partial negative charge of the oxygen and the partial positive charge of the hydrogen. And we can represent this dipole moment in the chemical bond by pointing in the direction of the electron migration. So over here, if you look at this arrow, I have a positive end, and the electrons are migrating in this particular direction. Another thing you'll need to keep in mind is that the dipole moment is a vector quantity, meaning it has both magnitude and direction. Now, direction, I'm sure you all understand, but magnitude, well, let's take a look at this example over here. Carbon and hydrogen has a delta En value of 0.4. That's a pretty low value on the scale over here. As such, it has a low magnitude. On the other hand, oxygen and hydrogen has a fairly large value of 1.4, somewhere around here, and so its dipole moment will have a much larger magnitude. So in both cases, we have the same direction, but different magnitudes. Now, for the purposes of this course, you are only expected to qualitatively identify which bond has a greater magnitude, obviously the one with the higher delta En. And so we don't really need to go any further with the mathematics for vector quantities beyond this. Now let's differentiate between the two terms, polar bond versus polar molecule. You see, the presence of polar bonds within a molecule doesn't necessarily mean the molecule itself is also going to be polar. The molecule's geometry must also be taken into consideration. Let's take a look at carbon dioxide, for example. Here we have two types of bonds, the CO, or two bonds anyway, the OC bond and another OC bond. When we do the delta En calculations, we find that's 3.5 minus 2.5, 1.0. And of course, 1.0 is right in the middle of the polar covalent range, so we're pretty certain that it has polar covalent characteristics where the electrons are going to be shared unequally, resulting in a charge separation. So a partial positive charge for carbon, because it has a lowered En value, and a partial negative charge for the oxygen, because it has a higher En value. This charge separation results in the formation of dipole moments. So there's one dipole moment moving this direction for this OC bond, and another dipole moment moving in this direction for this OC bond. So as we saw earlier, individual bonds can have a net dipole moment, and so we call them polar bonds. But what we're looking at this point is, for the overall molecule itself, the entire molecule, is there a net migration of electrons moving in one direction or the other? And that tells us whether or not we have a polar molecule. To do this, we must first look at the geometry of the molecule. So we use Vesper to predict that carbon dioxide will have a linear shape, so a straight line. From there, we look at the individual dipole moments and add them up from head to tail to determine what the net or overall polarity or overall dipole moment is going to look like. Looking at carbon dioxide, we see that there are two dipole moments, one going this direction and one going in this direction. By adding these dipole moments from head to tail, we notice that there is no net migration of electrons, and thus no dipole moment. Now, I've drawn these two arrows side by side. I guess you could look at it in this way, where we have one dipole moment moving this direction and the second one moving in this direction. And so what happens is the start point is also the end point. Thus, there is no displacement, meaning that there's no change in position. It's like having two twins playing tug of war with a pair of electrons. Since both of them have the same strength, we have two magnitudes that are identical to each other, both going in opposite directions. So overall, the electrons aren't moving anywhere. There is no displacement. Similarly, although there are dipole moments within the bonds themselves, as a whole, this entire molecule is considered to be non-polar because there is no net dipole moment for the entire molecule due to its geometry. So yes, we do have polar bonds, but we do not have a polar molecule. Now please keep in mind, when you're adding vectors, it really doesn't matter which vector you add first and which vector you add last. Adding vectors is like adding numbers. It really doesn't matter if I add 1 plus 2 plus 3, or 2 plus 1 plus 3, or 3 plus 2 plus 1. In the end, we all get the same value. Similarly, as long as you add head to tail for all the vectors, it really doesn't matter where you start or who you end off with. In the end, the net displacement is what you're looking for, and that will be unaffected by the order in which you add the vectors. So when we look at water as an example, we notice that the chemical formula for water, H2O, is very similar to the chemical formula for CO2. Similar in the sense that they're both made of two elements, of which one element is doubled. So CO2, two elements, C and O, and there's two of these oxygens. Whereas with water, again, two elements, H and O, but there's two of these. This is a hydrogen element over here. However, due to Vesper predicting that H2O will have a bent geometry, we have totally different results with regards to the dipole moment. As such, it is very important that you know your Vesper theory. Again, we do our delta En calculations for the OH bond, which is the only type of bond I see over here. 3.5 minus 2.1 gives you 1.4, which is definitely in the polar covalent range. As such, there's a charge separation where the electrons are migrating from the hydrogen towards the oxygen in this direction. Again, each bond is identical, thus their magnitudes are identical as well, and differ only in their direction. And so when we do add their dipole moments, we see a displacement indicating a net migration of electrons. So here I've taken the left dipole and added it head to tail to the right dipole over here, and I have a net dipole moment towards the oxygen in this direction. So there is a net displacement, meaning I started off here, I ended here. Whereas with carbon dioxide, I start off here, and then after that I come back and I end back here. So there is no net displacement. In this case, there was no overall polarity for the molecule. Even though the bonds themselves were polar, the molecule itself was non-polar. In this case, both the bonds are polar and the overall molecule is considered to be polar. So just to reiterate my initial point about adding vectors, again, it doesn't matter which vector I add first, as long as you're adding them head to tail. So the first example, I added this vector first, and then this vector, which results in an overall net dipole moment in this direction. Similarly, when I add this one first instead, and then go with this one second, I still end up with the same overall net dipole motion, which is in the upwards direction. Sadly, as the molecules become more and more complex, it becomes more and more difficult for you to imagine how these dipole moments are going to be added up in 3 dimensions. But once again, don't freak out. For the purpose of this course, you are only required to qualitatively indicate whether a net dipole moment exists. What I mean is, for instance, over here, take a look at this particular molecule, sulfur tetrafluoride. In this case, there's 4 dipole moments altogether. One pulling this direction, one pulling this direction. Notice how these 2 dipole moments will be canceling each other out because they have the same magnitude. But I do have one dipole moment pulling this direction and one pulling this direction. So ignoring these 2 because they cancel each other out, imagine 2 children trying to pull you apart or pulling you away. One is leading you down this aisle, another trying to lead you down this aisle. In which direction will you go? Well, straight ahead, so long as these 2 atoms are pulling with the same magnitude, just because these 2 will cancel each other out. On the other hand, with this one, we have 3 dipoles, and each dipole will have the same magnitude, going this direction, this direction, this direction. Let's take a look at it in 3D for a second. So looking over from the top view, we see that this fluorine atom is pulling in this direction, while this is pulling in this direction, and this is pulling in this direction over here. Since they're pulling in this particular plane anyway, in all 3 different directions, there is no net movement here. But if we rotate the atom in this direction over here, we do see that the net dipole moment will be going downwards. It will be moving down. From this plane, in all 3 directions, you aren't going to be moving anywhere in particular. They all cancel out because they're all moving in different directions, or opposite directions anyway. But the moment you pull it down this way, you notice there is no net motion pulling it back over here. Instead, everything's being pulled down, and so the net dipole moment is in the downward direction, as indicated in this particular drawing. All right, so the net dipole motions in this particular plane cancel out, but overall we are going to move downwards, and so the net dipole moment is in this direction, where the electrons will be mostly partially negative here, and this molecule will be partially positive at the top. All right, so let's try a couple examples. Let's see if sulfur dioxide is going to have a dipole. So is this molecule polar or non-polar? First step is to draw out the Lewis diagram for this. So for Lewis, we first find out how many electrons does sulfur have. Looking at the periodic table, it's in group 16 or 6A, and so it should have 6 valence electrons. So here I've drawn 6 valence electrons. Oxygen, on the other hand, also in group 16 or 6A, so it also has 6 valence electrons. And so I've combined them together into a lovely Lewis diagram. So this is one bonding pair of electrons, here's another bonding pair of electrons, here's one bonding pair, here's another bonding pair, and this would be a lone pair of electrons. Referring back to my VSEPR chart, I see that SO2 seems to have this particular shape, or this particular geometry, where we have one lone pair of electrons at the top, and the central atom is bonded to two other elements at the bottom over here, the two oxygens, and also the lone pair. So apparently it's going to have a bent or angular shape. I'm not even writing anymore. There we go. Bent or angular. Checking the EN values for oxygen and sulfur, we see that it's a 3.5 versus a 2.5, which makes a 1.0 delta EN, and therefore this particular bond, LOS bond, is polar covalent. As such, we show our charge separations. Whoops. It should be going in this direction, where the oxygen with the higher EN value grabs onto the electrons. So electrons are migrating in this direction for both these bonds, since both bonds are identical. And they should have the same magnitude. And of course, as you can see, we have polar bonds. Let's take a look and determine whether or not we have a dipole moment by adding the vectors head to tail. Again, it doesn't really matter which vector you add first. In the end, the net dipole moment is in the downward displacement or downward location. So overall, this molecule over here tends to be partially negative, whereas the top portion of the molecule tends to be partially positive. Thus, we have found that SO2 has a bent shape, and it is definitely a polar molecule containing polar bonds as well. For our next example, let's take a look at ammonium. What I would like you to do is pause the video at this point, try it out for yourself, and compare your answers with mine. Alright, so hopefully you've had a chance to pause the video and try it out yourself. Let's take a look at it. Now nitrogen is in group number 15, or 5A, and thus must have 5 valence electrons. So here I've drawn nitrogen with its 5 valence electrons. Hydrogen, of course, is in group number 1 and has 1 valence electron. Now since there are 4 hydrogens, what I'm going to do is I'm going to draw them all around. Here's a hydrogen donating an electron here. Here's another hydrogen. Here's another hydrogen. But oh wait, I can't put an extra hydrogen here because nitrogen already has 8 valence electrons and it's already stable. By adding an extra electron here, it becomes unstable. Thankfully, you may have noticed that there is a positive charge on ammonium. So that means ammonium has lost 1 electron in order to become stable. And that's a good thing in this case because we don't need this electron over here. So now we've got a nice stable compound, NH4+. Let's take a look at it and see what kind of VSEPR geometry it should have. Looking at this chart, I need to have a compound where I have 5 atoms all together. That would be this one over here, one of these guys. So 1 central atom and 4 atoms all around it. These two, it can't be these two because they have 2 lone pairs in this one, 1 lone pair in this one, and no lone pairs here, which matches exactly what we have in this case. So these are bonded pairs of electrons, bonded, 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 and bonded. There are no extra floating electrons around the central atom, and so the tetrahedral shape seems to fit NH4+. Let's quickly look at the delta EN values. 3.0 minus 2.1 gives you 0.9, and so it is a polar covalent bond. In this case, the nitrogen is more electronegative, so the electrons, or the dipole moments, tend to move in this direction. Here, and here, and here. Now, it is a tetrahedral shape, so we should draw this in 3 dimensions. I may have neglected to do that in the last example, my apologies. But this one is definitely in a 3-dimensional space. So what happens is, anytime you have a straight line, it means that that bond exists on the plane of the paper. Any dashed lines like this means the hydrogen is actually sinking into the paper, whereas a solid line like this, and I guess you could fill it in if you want, means it's coming out of the paper. So this hydrogen is coming out of the paper, this hydrogen is going into the paper, while these two hydrogens lie on the same plane as the paper. And that's how we draw a three-dimensional Lewis diagram. Now in both cases over here we have a polar covalent bond, and as we saw earlier, because all the bonds are of the same magnitude and all are pulling towards the central atom, there is no net dipole. All of them seem to cancel out. So this one would cancel out with this one would cancel out with this one, and all the vertical components and the horizontal components would cancel each other out. So in the end, this compound has polar covalent bonds, but it is not polar covalent. I'm sorry, what I meant was it's not a polar molecule, as there is no net dipole motion. The displacement, well, there is no displacement. Where you began is where you end up. So stay tuned for our next video clip, where we'll discuss why we have to determine whether or not a molecule is polar or non-polar in nature, and how does that affect its physical and chemical properties.